Previously, in our proof of the weak Nullstellensatz, we have used the following theorem, which is sometimes also called the weak Nullstellensatz. The theorem says that if L is a field that is finitely generated as a k-algebra, then it must be finitely generated as a k-module. In other words, it's a finite field extension of k. For that, we need to use the following theorem called Noether normalization. It says that every finitely generated k-algebra that is a domain must be integral over some polynomial ring. This is not hard to prove using induction, because for example, if the AIs are already algebraically independent, then A itself is a polynomial ring. Otherwise, we can suppose that they are algebraically dependent with some relation f, and we can argue that without loss of generality, we will be able to assume that one of these leading coefficients of some of these AI is going to be non-zero, so we can view this as a monic polynomial in the variable an with coefficients in a1 to an minus 1 over k adjoining the remaining AIs. And now by induction hypothesis, this ring here is integral over some polynomial ring, so by transitivity, an is also integral over some polynomial ring. And thus we have that every domain that is finitely generated as a k-algebra must be integral over some polynomial ring. Now coming back to our theorem, we suppose that L is a finitely generated k-algebra that is also a field. So from Noether normalization, we know that L is integral over some polynomial ring. Now, as L is a field and this extension is integral, this polynomial ring here must also be a field. That is a theorem from commutative algebra. But this polynomial ring here is a field if and only if the transcendence degree is 0. i.e. this must be the field K itself, and we see that thus L must be algebraic over K. Since L over K is algebraic and finitely generated, we see that L must be a finite extension of K. Thus we see that for a field, being finitely generated as a k-algebra is the same as being finitely generated as a k-module. Actually, since we still have some time, let us actually prove this theorem. Let us just prove this direction which we used. Right, so we are supposing that B is a domain and A is a subring such that B is integral over A. We want to show that if B is a field, then A must also be a field. In our case here, we have used that to deduce from the fact that L is a field that this polynomial ring must be a field. So let us see why this is true. Alright, so let us take some non-zero element f in A. We want to show that it's gonna be a unit in A. Now since A is a subring of B and B was assumed to be a field, we know that f has an inverse in B. Thus, we only need to show that this inverse actually lies in A. Here is where we use a hypothesis that B is integral over A. Right, so since B is integral over A, this inverse must satisfy some monic polynomial with coefficient in A. If we multiply this polynomial through with f to the n minus 1, then what we get is that f inverse plus something in A is equal to 0. So f inverse must lie in A, as we claimed. Thus we see that if B over A is an integral extension, then if B is a field, A must also be a field. In particular, if a field L is integral over some polynomial ring, then this polynomial ring must actually be a field and thus must be isomorphic to the ground field K. Since by Noether normalization we know that every finitely generated k-algebra is gonna be integral over some polynomial ring over K, we see then that for a field, being finitely generated as a k-algebra is equivalent to being finitely generated as a k-vector space.